Hello, welcome to the channel. So this is the part 2 of the series of solar radiation, chapter 3 of SP SUKHATME. So let us continue our lecture. And in today's lecture, we will try to draw the spectral distribution of extraterrestrial solar radiation. Now, first of all, if you are having doubt with these terms, extraterrestrial, so I do recommend to watch the part 1 of the series. I have clearly explained what is extraterrestrial solar radiation and what is solar constant. So if you're interested in that part, please do watch the part 1 of this series. Now in this part 2 series, our first aim is to draw the spectral distribution of extraterrestrial solar radiation. So let me give you a brief idea about it. It is a graph between the wavelength of the solar radiation and the monochromatic emissive power. Okay, so it looks something like this. So how are we able to draw this graph? So today we will go through this. Now, before we discuss about the spectral distribution, let us first of all have a brief idea about Planck's law and Stephen Boltzmann's law. Uh, Planck's law. Now, Planck's law stated that the spectral emissive power of a black body is given by this is known as the spectral emissive power, and this is also known as monochromatic emissive power. Monochromatic emissive power, and the unit is a watt per meter square. Okay, micrometer. Now we will discuss about it, the unit of monochromatic emissive power. Let us first discuss about the Planck's law. What is Planck's law? It stated that the monochromatic emissive power, or this spectral emissive power, this is equal to 2 pi c1. First of all, let us have a brief idea about it. So Planck's law stated that this is a function of wavelength and temperature. Okay, so this is wavelength and this is the temperature. Okay, so the formula was 2 pi c1 divided by lambda to the power 5 e to the power c2 by lambda t minus 1. Okay, so this formula was given by Planck, so that's why it is known as Planck's law. Now as we can see from the formula, this c1 and c2, they both are constant. Okay, c1 and c2 are constant, and the value of c1 is a 0.596 into 10 to the power minus 16 watt meter square, and the value of c2 is 0.014387 meter Kelvin. Okay, so c1 and c2 are they are constant, so the monochromatic emissive power becomes the function of lambda and the temperature T. Okay, now first of all, this monochromatic emissive power that we are calculating, this is for specifically black body. Okay, now this is specifically for black body, that's why we have written B. Okay, the B represents black body, lambda represents the spectral or monochromatic, that is for a particular wavelength, and E means the emissive power. Okay, now so if you want to explain someone that what is Planck's law, so in so it means how much radiation energy, sorry, how much amount of radiation energy a black surface or black body, okay, emits of a particular wavelength per unit area per second. Okay, so monochromatic emission power or spectral emission power, this is EB lambda. It means that how much amount of energy, if I'm talking about the how much amount of radiation energy, so it means I'm taking the value in joules. A black surface emits of a particular wavelength, okay, per unit area per second. Okay, so it means that how much amount of radiation energy a black surface emits for a particular wavelength per unit area per second. Okay, so this can also be written as watt per meter square micrometer. So this is the unit of monochromatic emissive power or spectral emissive power of a black body. Okay, so this was given by Planck, so that's why it is known as the Planck's law. That is, let us consider this body to be a black body. Okay, now first of all let us have a brief understanding of what is black body. Black body means the emissivity is 1. Okay, emissivity is 1. Okay, so we will have a detailed lecture about what is black body, but just for this lecture, just keep in mind that the emissive power of a black body, sorry, the emissivity of a black body, it is equal to 1. Okay, it does not means that the color of the body is black. No, for example, ice is considered as a black body. It is a perfect emitter and a perfect absorber. So that's why it is called a black body, and its emissivity or absorptivity, they both are equal to 1. Okay, so for a black body, the amount of energy, radiation energy in joules emitted per unit wavelength, okay, emitted for a particular wavelength, okay, per unit area. Let us suppose this is the unit area per second. Okay, so that means a unit area, how much amount of energy, radiation energy, a unit area emits, okay, and for a particular wavelength per second. So this is what Planck said, and he gave us the formula for uh, emissive power of a black body, monochromatic emissive power of a black body. Okay, now the second most important law in radiation is Stephen Boltzmann law. Now Stephen Boltzmann law, what he did is what he simply integrated the formula given by the Planck's, and gave us the formula for emissive power of a black body. So this is emissive power of black body. And according to the Stephen Boltzmann law, this is equal to integration 0 to infinity EB lambda d lambda. Okay, so when I integrate this, I get the value sigma T to the power 4, where T is the absolute temperature in Kelvin, and sigma is the Stephen Boltzmann constant, and its value is 5.67 into 10 to the power 8 watt per meter square Kelvin to the power 4. Okay, so these both laws, Planck's law, Stephen Boltzmann law, they both are very important. Do keep in mind, Planck's law was for spectral emissive power or monochromatic emissive power. That means for a particular wavelength, it gives us the value of the radiation energy, the amount of radiation energy. But Stephen Boltzmann law, it gives us the emissive power. Okay, so that's why we have integrated it. You will understand it when I draw the graph. Okay, now we assume that that our sun is a black body. Okay, now this is an assumption. We assume that the sun is a black body. Why? Because we want to calculate the temperature of the surface temperature of the sun. The surface temperature of sun. Okay, we need to calculate this value. How we will calculate this value? Using Stephen Boltzmann law. Okay, now I'm directly writing the value, but if you want to see, you can see other YouTube videos where people have already calculated or how they have calculated the surface temperature of the sun using Stephen Boltzmann formula. Okay, you can go and watch that video, but I'm directly writing the value. The surface temperature of the sun using Stephen Boltzmann's formula is 5779 Kelvin. Okay, now let us have a look into this Planck's formula. EB lambda is equal to 2 pi C1 lambda to the power 5 e to the power C2 by lambda t minus 1. Okay, now we have assumed that the sun is a black body. Okay, and we have calculated the value of temperature. Okay, we have calculated this value t. So once I have calculated the value of temperature, now what is left? I need the value of lambda for calculating the value of monochromatic emissive power. Okay, now for different value of lambda, I can have we can have different value of EB lambda. Okay, so since we have calculated the surface temperature of the earth, sorry, of the sun, now for different value of lambda, I can calculate the different value of monochromatic emissive power. Chromatic emissive power. Okay, now uh, first of all, let us put the value of lambda equal to 0. Now what we will get? EB lambda will be equal to 0. Why? Now if I put the value of lambda here 0, e to the power infinity is infinity. So that's why 1 upon infinity it becomes 0. Okay, so for lambda equal to 0, EB lambda is 0. So if I draw the graph between EB lambda and the wavelength, for 0 value of wavelength I have 0 value of EB lambda. Okay, now if I increase the value of lambda, definitely the value of EB lambda will also increase, but up to a certain value, then it will decrease and will become asymptote at this point. Asymptote at this point. Why asymptote? Now first of all, what is asymptote? Asymptote means that it tends towards 0. It is not equal to 0, that it becomes parallel to this lambda axis. Okay, so it kind of moves in this direction. That is known as asymptote. Okay, so the graph that we have obtained is known as the spectral distribution of extraterrestrial solar radiation. Okay, solar radiation flux. Let me redraw this. This is somewhat like this. Okay, now let us study the graph. As we can see, we have a peak value, and the peak value we obtain is it is at a wavelength of 0.48 micrometer. Okay, so do remember the peak value of EB lambda, that is known as EB maximum. It has a wavelength of 0.48. Okay, now as we all know that the solar radiation also has the visible spectrum, that the visible light. So it is between 0.4 micrometer to this is 0.7 micrometer. Okay, so let me write it here. First of all, the EB lambda maximum monochromatic MSA power maximum value, its maximum value is at wavelength of 0.48 micrometer. Okay, and also the visible spectrum or the visible light ranges from the value of lambda 0.4 to 0.7 micrometer. Okay, now let us have a brief idea about this graph, what is happening in this graph. So for different value of lambda, let us calculate the monochromatic emission power. Okay, now for lambda equal to 0.2, the value of EB lambda is very small. Okay, so we can neglect it, which means, and let us suppose that this line represents 0.2. So here the value of EB lambda is very small, it is almost equal to 0. Okay, so that's why we do not calculate the value of at EB, calculate the value of EB lambda at lambda equal to 0.2. Okay, but at 0.3 it has a value of 528, and at 0.4 the value is 1702. Okay, now this value keeps on increasing. Okay, and as we have already discussed, its maximum value is at 0.48, which is equal to 2055. Okay, now after that, if we increase the value of lambda, this value will decrease, that is at the value of 0.6, this is 1720. Okay, now let us define another term, d lambda. It is the percentage of radiation obtained up to a certain wavelength. Okay, now what does it mean? uh, what is d lambda? Now d lambda is the ratio of ISC and integration 0 to lambda EB lambda d lambda. Okay, now let us suppose at this value at 0.4, now this much amount of area, this is equal to this value. Okay, and ISC, as you already noticed, 1367 watt per meter square. Okay, so d lambda is the ratio, is the percentage, or it is considered as the ratio of the radiation obtained up to a certain wavelength. Okay, so up to a certain wavelength means, let us suppose I'm calculating up to 0.4, so area behind 0.4 is the numerator, and the denominator is the ISC, so that is the ratio. Okay, so as we know that this ratio will also keep on increasing, so at 0.3 it is 2.12, at 0.4 it is 6.4846, and approximately at the value of 4 micrometer, I mean the lambda value is 4 micrometer, uh, the t lambda is approximately 99.16. Okay, so what we conclude is that the area under the graph, the area under the graph, this graph, okay, this line is almost 99.16 percentage at lambda equal to 4 micrometer. Okay, so this value is also important. That means at a value of 4 micrometer, the d lambda is 99.16. Okay, so thank you for today's lecture. Let us continue with this series forward.